All right, so what I want to talk about now is we're going to talk about neuronal membranes as sort of our example cell type. It is the only cell type we'll talk about. We are actually not going to talk about action potentials, depolarization, all of that jazz that you usually get somewhere in biology, and maybe possibly again in 418 they'll cover it. Who knows? But I've cut it in the interest of time. But neuronal membranes will be our sort of example membrane for looking at all of this stuff. Okay? Neurons consist of a cell body with dendrites, a single axon that ends in sort of a synapse that can then interact with some other neuron or cell type of muscle, neuromuscular junction to send a signal. They're the best cell type, first of all, because that's the cell type I worked with for like 5 straight years. Plus, they're cooler looking than like boring old round cells. Right. Neurons have an electric potential difference across their membrane, essentially meaning the charge on the inside and outside is not the same. Like at rest, we expect there to be a difference in potential across the neuronal membrane. Okay. And I'm telling you that that difference is there's an accumulation of negative charge on the inside. This is because there are a lot of proteins on the inside, and these proteins are negatively charged. Okay? And so there's excess negative charge on the inside, excess positive charge on the outside. And so that's sort of illustrated here. We know we also have a couple of key ions coming into play. So we have a difference in concentration of positive sodium, potassium ions and negative chloride ions on either side. But again, what really dictates this difference, this overall resting difference across the membrane, is these negatively charged proteins on the inside. We call the voltage difference across the membrane membrane potential, and we give it the notation E sub m. Okay? So if you see E sub m in your equations, this is the membrane potential. Hint, you probably don't even want to use any equations with E sub m in it if the question isn't asking you about a cell at all. If it's like, oh, hey, there's metals in some liquid. Don't use this one. Nice and easy. Okay? Another sort of convention, okay? A convention for our textbook and that we'll use here is that the membrane potential is calculated as the difference on the inside minus the outside, okay? So one of the things that I'm going to tell you is important to think about when I'm asking you to calculate a difference in free energy, a difference in potential between when we did chemical potential and we were talking about the difference between 2 areas, or on homework 6. Final minus initial is always the way you should think about any of these differences. Where am I going minus where did I come from is a better way to do it. For your textbook, in minus out is how they've set up the membrane potential. But if I'm moving out to in, signs need to flip. Things need to flip. Okay, so just keep that in mind. So when we say that the resting membrane potential is negative 70 millivolts, it's because we've done inside minus outside. The inside is negative minus the outside. Okay? And the resting membrane potential, what resting here means is that we have reached sort of a steady state, no net flow of ions. Okay? So ions can flow in and out, but from a macroscopic view, those concentrations are staying the same. And this is the difference we would see in voltage between the 2 sides.